All right, I think we're ready to start, so we're gonna get going here. I'm gonna give you a fair warning, like this conference has enterprise in it, right? So I'm gonna give you a fair warning, a lot of this stuff isn't probably enterprise ready, meaning there is no Active Directory integration. Everyone likes Active Directory. All right, so, but the goals of this talk really are to provide an overview of CoreOS and Kubernetes, not in the salesman type of way. I'm not going to show any charts going up and to the right. We're going to just talk about like open source tech that will enable you to kind of do some of the things you've been reading about in white papers or seeing in some conference talks. So I think we're getting to the point now where a lot of those bits and theories are actually becoming practical and something you can actually download. So that's going to be the high level goal of this talk. And then we're going to do a live demonstration of Kubernetes in action, right? So we're going to do less hand waving and then actually try to deploy what I consider a real world application, right? And then I want to demystify some of this stuff. So there's a lot of like large tools that aim to solve a lot of these problems, but they're really, really hard to install, right? Those are like consultantware, right? It's enough you can read the site, you download, and it's like call a consultant. And this stuff is much easier than that. This is stuff that you can actually run on your laptop consultant-free, right? So I gotta frame your mind first, right? So the idea of this, if you guys are sysadmins in the crowd or developers doing ops work, the way you need to view this, I think, is imagine how you would design your infrastructure if you could never log in, ever, right? And the idea here is like, if you have like a Roku box or something at home or a Fitbit on your wrist, you haven't been itching to log into it, right? Like you haven't been trying to put your SSH keys in there, get your Emacs config right. And we see that infrastructure can also be managed this way as well. We can think of the OS as the firmware running on a collection of machines, and you try to avoid this idea of just logging in to fiddle with the bits, right? I'm gonna see if that's actually possible. Another set of level setting is what is a container? This is just like crazy where people are thinking about containers these days. Like it's like secret sauce and unicorns. It's not any of those things, in my opinion. They're not golden images. So I think by default, most people's experience or initial experience with containers have been using a tool like Docker, which is a fantastic tool. But a lot of people got introduced to it all the wrong way, right? They have a Docker file that has like from big operating system at the top. So now you start with this like 1 gig operating system, and then you add your 15 kilobytes of source code, and then that becomes your container. That's like crazy, right? So a lot of times the containers we build at CoreOS, and there's a lot of other companies with more experience, their containers are really small. Sometimes just the executable binary, if they're self-contained, like a Go binary. And if you're running a Ruby app, maybe just the dynamic libraries that you're linking against the runtime in your app. So there's no reason why you can't get containers down to about 20 megs, right? So that's the thing to think about. So when you think about it and frame it in that context, we're talking about application containers here. These are just like Unix processes, not lightweight virtual machines, right? People that think they're lightweight virtual machines, you will be on CNN explaining how you got hacked because they don't contain at that level, right? You have to kind of be aware that these are just Unix processes. They do give you some containment, which is awesome. So a lot of people are running virtual machines solely for the reason of being able to install multiple versions of the app at the same time, right? Have you ever tried to do this with RPM? Like yum install app version foo, and they all live in the same space, it just doesn't work. You just like upgraded all your servers when you really wanted both of them. And then you get into some JBoss magic with symlinks and tarballs and warfile deployments. All of that is mainly because you don't have any containment. So this is what containers bring to the table. They give us that file system namespace, so that way we can actually contain things and have our dynamic library specific for each application. That gives you a new way of thinking about carving up a server versus immediately running to virtualization. So with all that in mind, an application plus its dependencies equals an image. So that's the thing you see on a Docker registry where people take their application, all the dependencies it needs, and then you can deploy it to a system that's running a container manager. Very similar experience to the way you operate your mobile phone, right? Imagine if we let sysadmins design the deployment mechanisms for a phone, right? Your battery life would be about 22 minutes. It'll probably be running Popular Chef, and just deploying anything would just be this crazy endeavor, right? Infrastructure is code for your phone. Like, this is not gonna work. So we're not doing that. We want to treat the servers the same way. And at the end of it, all these container runtimes provide you a runtime environment. They usually make some default choices for you, like how you use C groups, how you use namespaces, and what your environment bars look like, right? So that's like containers in a nutshell. It took system, service Apache start to another level and gives you some containment. And you introduce things like network namespaces. It feels like a virtual machine because each of your apps now have an IP address, but it does introduce a lot of complexity. And that's what this talk is about. When you start going down the container route and you start having 100 IPs per server now, things get complicated. You got to figure out what those things are. So at the foundation, containers, since they're not magical, they still require operating systems, right? A lot of people think the operating system will disappear, but it turns out you still need one in some cases, right? Unless you're in like OSV world and you have microkernels. But in this case, at CoreOS, we started with an OS that's just stripped down of everything. And this is what a lot of people have been doing by default, right? You take a Debian system and you just remove everything you don't need. Maybe you leave like a VLC on there so you can play videos or something. I'm not sure why you have Bluetooth enabled on your servers, but that's just what happens by default. So we have this minimal image, and then we don't have a package manager, right? So I've seen user studies where people take CoreOS and they're like, yum, and apt-get, and it just doesn't work. And the reason why we do this is so we can actually do atomic updates of the system. We can't have you going around there just installing things willy-nilly. We kind of want to have a contract between you and the operating system. So the fact that we don't have any of our users depending on our local Ruby install, a local Python install, we're free to upgrade the system whenever we please. This is like what Chrome started doing, right? You downloaded Chrome, and it's like, I'm going to update your browser. Not asking for permission, it's like, I'm going to update your browser, whether you like it or not. And the good thing there is that we kind of move things faster into the future, right? If we didn't have that, I think we will all still be on ActiveX right now, if Chrome didn't hit the scene. And then we have these multiple partitions, so we kind of work like your network gear, where we can update a partition in the background, and when it's ready, we can coordinate reboots throughout a cluster. And we'll talk about some of the components that allow us to do that. Next is Kubernetes. The thing I like about Kubernetes is that a lot of times when we talk about all of this infrastructure stuff, a lot of people come up to you and tell you a really cool story, right? They tell you about 58 like little utilities that they've stitched together into this thing. As long as you don't touch it, it works fantastic, right? But no one really cares, right? You tell someone, look, I just need my app deployed. Like, how can I get that? I don't want to know about infrastructure as code. I don't care about the thing you found on GitHub. Are you going to get my servers deployed or not, right? I don't care. So Kubernetes is a clean separation of these concerns, right? There are people that rack machines in a data center. Kubernetes doesn't try to deal with that problem. There are people that provision VMs via APIs. Kubernetes doesn't deal with that problem, right? Those are separate concerns. Now, a lot of tools try to conflate these concerns, and it looks very convenient in the beginning, but it falls apart really quickly when you start to scale different concerns, right? Because if you give someone access to a tool that does it all, well, you give them access to everything, switches, the VMs themselves, and the underlying infrastructure. That's not what you want. You kind of want that Heroku type model where you just say, hey, here's the APIs to the infrastructure. I got this other part covered. So no opening tickets to tell me you want a new server, because I actually don't care. Like, spin it up. We have some hardware that we have allocated to the cluster. You can just define things. I'm going to see how Kubernetes provides primitives to separate those concerns. And this is what we talk about when we talk about large scale, right? Some people say, yes, I have large scale because my Amazon bill is $8,000, right? That's not large scale. You just have a bunch of VMs, right? That's all you have. In a larger scale setup, when you start to talk about the hundreds of thousands of machines, you start separating some of these concerns. So Kubernetes is API driven. Everything is truly defined in a spec, right? So you don't see code in there. There's no for loops. It's not Turing complete, any of that business. Your whole goal is to encapsulate all the things that you know to do, all the good patterns of operating a platform. You put the intelligence in the binaries that run the infrastructure, right? Instead of having everyone express themselves the same way over and over again, I've seen companies that have more configuration management code than application code. Like this is off. Like we didn't sign up to be Puppet developers, right? And then the next thing you have is a bunch of little agents with specialized responsibilities that live on the network and enforce your desired state that you specified. And then you have another piece, which is like a lot of people that have run in like cloud environments like Amazon. You have these controllers that keep it up to date. So one of the sweet things about most configuration management tools, they kept things up to date, right? You specified it, and every 30 minutes or so, it would try to put things back, right? But there's a problem there. If you have 100,000 machines, and every 30 minutes, some people are taking a month to do a rollout. That's just not gonna work, right? So we're at a new level of scale, different set of tools for this problem. So nothing's wrong with the existing tools. We're just talking about a different problem. And then another thing that's nice about Kubernetes is it uses labels to identify everything in the system. That's really, really powerful, and we'll see what that looks like in action. So let's break it down before we jump into a live demo. There's not a lot of slides here, but I do want to make sure you understand what the components are doing, right? So Kubernetes itself has 4 primary things we're going to talk about now as first-class objects in the cluster. Number 1, there's a node. Things get scheduled to a node. How many people have a scheduler at their job? You all do, actually. I've watched them. I call it the meat cloud. You have a bunch of human beings that need to figure out what something needs to run. They grab the database, a spreadsheet, and they say that this app runs here, this app runs here, and they've scheduled the thing. And some people are fast, too. They're like hotkeys. Excel, boom, update, down, save, update, into SharePoint. It's like, sweet, this is like distributed because 3 of us can do it, right? So you have this badass, awesome, highly distributed, highly available because everyone's wearing pagers, scheduler, and everyone like that is like the scheduler most people use, right? We're gonna try to take that scheduler and just put it into the system, right? And I show people this, they're like, so what am I gonna be doing now? I'm like, I don't know, Seriously, because some sysadmins have actually taken the time to learn how to build a pivot table. Like when you learn to build a pivot table, this is the holy grail of Excel. If you don't know how to do a pivot table, go look it up and you're gonna be like, whoa. All right, and then the next primitive is a pod. Now a pod is unique because a lot of times when you're doing this work, you need containers to be co-scheduled at the same time. And there's some cases where you want things like a local Memcache to be scheduled locally with your app, right? And in more traditional or more typical setups, what you'll see is you have this Ruby on Rails app, and there's like a little script thing that does the migrations, right? And if you put them in separate containers, it's really hard to kind of get your scripts to make sure they land in the same place. Pods solve that problem by allowing us to couple the things that make up our app. So if you have like 5 components that make a logical application, you put them in the same pod, and then that pod gets scheduled as a single unit around the cluster. And then we have replication controllers. These are the things that give you the ability to say, I need 3 of these things, or 6. And if 3 of them go away, well, it just brings them back, right? And then a service. So service is very similar to like a VIP, a virtual IP. So if you have maybe 8 of these pods running somewhere in the cluster, how do you get to them, right? You don't want to track all those IPs because the nice thing about having an automated scheduler is that those things can move at any time. So what we do in Kubernetes is you have a service, and a service actually does dynamic lookups for those pods at request time, right? You can do some fancy things like caching. But the idea here is that you make a request, this thing does a label query since everything has labels, and you can kind of get into some fancy set theory if you think about it, because you can have like a new version and the current version having overlapping labels and have a service watch the overlap. That way you can do rollouts, and we'll see this in a demo. Nodes, they're responsible for Flannel, which is our overlay network, and we're going to see here. We have a couple ways we can do this. We have an actual overlay network where we do some L2 over L3, or we can actually just do something simple where we configure the Docker bridge and we update a central routing table in some fancy router somewhere, right? And we get out of the data path. We just influence where the packets go by updating routes on the machines. Docker, the standard runtime engine that exists on CoreOS and Kubernetes. There's a kubelet, and the kubelet is the thing that takes jobs from its queue and ensures that they're running locally, and by talking to the Docker API. And the proxy runs on every machine, and the proxy gives you the ability to say, if you have 100 machines and only 3 pods that make up this application, you can hit any of those machines, and the proxy will send you to wherever the pod is, right? This makes things really convenient for you. And like I said, everything is described in a manifest, or a spec, if you will. Here's what a node manifest looks like. So imagine someone racking machines in a data center, right? So you have this server. Okay, you have this virtual server that runs in the cloud, and you have a bunch of containers running on it, right? And you can use one of these node manifests to say that this particular server has these sets of resources. That kind of gives the scheduler a hint on how many pods it can run. All right, so you can define these nodes this way. Here's a pod, and a pod represents a logical application, one or more containers, shared volumes. So if you have that Rails migration script, it can look at the Ruby code. Sometimes people need the Ruby code in order to do the migration. And you can kind of reach into the mount namespace to see that. And when you're in a pod, you actually share the same IP address, so you can address things in your pod on localhost. You don't have to go search for them. They're identified by IDs and labels, and they're optionally managed by replication controllers. Just because you move the containers doesn't get you magic. If you're running Postgres, that is your single point of failure. You can set up some replication stuff, but it doesn't change the story. So in those cases, I can't just move Postgres and leave the data behind. It's going to be really embarrassing. What you have to do in that case, you got special snowflakes, right? If you're using special snowflake apps, they're going to make the servers they run on special snowflakes. You can't avoid it right now. There are ways you can do it, but most people aren't there yet. Here's what a pod manifest looks like really quick. The main thing here is I'm saying what I want the desired state to be. I can have one or more containers to create this pod, and I give it some labels. Ooh, edible slides. All right, a replication controller's job is to replicate a set of pods, right? And it creates pods from a template. And it ensures your desired state is always running. It doesn't mean there's always going to be 3. It might be 2 and then go to 3. It might go to 4 and then go back to 3, depending on the conditions of the network. The whole goal is just to keep the desired state. Here's what a replication controller looks like. The interesting bits here is that there's a pod template that you embed. And this is kind of like you do in Amazon when you use like an auto-scaling group, where you kind of define what the AMIs need to look like, right? And attach them to a load balancer. Very similar semantics here. And all of this is really designed to run well outside of the cloud as well. This gives you a chance to like run on bare metal, like the way a lot of the larger orgs do. And then lastly is the service. So service provides you a convenient method of true service discovery, because Kubernetes is the thing actually scheduling pods. So it knows where they are, right? So you'll see some service discovery techniques where people like, I think of it equivalent to like web scraping HTML. Like you deployed it and then you go scrape the system to figure out where it is. Like you put it there. What are you reverse engineering? Stop. So Kubernetes actually gives you semantics to do that. And that proxy thing helps because you can do the label queries automatically. And here's what a service manifest looks like. All right, now you guys have been framed with all the components in Kubernetes. Let's do a real world example. Now this is a live demo, so if it fails, I'm probably going to try again, and if it fails again, I will give up. But the goal here, I'm just being honest, it's real world, no videos. So real world, I used to do these in the cloud, and people are like, the cloud is easy, you can do anything in the cloud, right? I said, okay, we'll do very close to bare metal. So I have my laptop, and it's made of metal. And what I've done here to take this step further, I took my VMs and my virtual machine, and they all have the Pixie firmware burned into their NICs, so they will Pixie boot, and they won't like use a CD or no install. So we're gonna try to mimic what happens in a data center here. But I do have storage drives in order to persist the containers when I create them. Can't run them all in memory. And then I need cross-host communication. So a lot of people's experience with like Docker by default doesn't work because 2 host containers can't talk across the board. Final will take care of that. So this is my infrastructure requirements. And here's the app itself. This is PGView. There's a little Go application, and its job is to tell you about your Postgres service, right? You can probably start a startup on this if you want to not make money, but it's a real service nonetheless. The application requirements here is I want it to be horizontally scalable, right? This is the stuff your salespeople tell potential clients that you probably can't do, but it's all right. We're in that business. We also want a dedicated Memcache instance per application. So if I have 6 of them, I want 6 Memcaches configured and that thing ready to talk to it. And I also want to use a Postgres database. Now, the operational requirements are automated service discovery. I don't want to be wiring things up. And zero downtime application upgrades. Now, this is hard. I see a lot of like sites say 5 nines of uptime. Have you guys ever seen that, like 5 nines? How many people know how much downtime you can have in a year to get 5 nines? 5 minutes. So I asked people, it's like, okay, how do you handle when things break? And they said, well, we got pagerduty, it's awesome. It alerts people really, really quick. I said, all right, let's just walk through it. You get the pager alert, you wake up, the clock's running, 2 minutes in, you SSH in, you got hotkeys again for the spreadsheet. You found the service, you log into the service, you reboot the service, it's back up. You're like, sweet! Now you're down to 2 minutes and 30 seconds for the rest of the year if this happens again. So it's really hard to hit 5 nines if the systems aren't trying to heal themselves first, right? Maybe a little bit of over-provisioning and some auto-healing, right? You can't just be in React mode. You gotta have a system that's reacting for you. And we're gonna try to see if we can do something close to that. And here's what PGView does. It's a Go RPC application. So if you hit it and you hit one of the endpoints, it'll tell you a lot of things about Postgres formatted in JSON. So for some of you that me on the other side of my age bracket, these are very exciting languages for you. No, like, you gotta remember at some point, if there was Hacker News like 40 years ago, this would have been like all the rage, like Ada is gonna crush COBOL or whatever. But for some people, this is job security, so we shouldn't laugh at them. So now let's switch to Kubernetes in action, all right? So this is the part that makes me cringe because a lot of times, I don't even think I booted my machines here. So I'm just gonna I'm gonna bring up each virtual machine, right? I'm gonna start with etcd. So this is the thing that gives us the consensus on the cluster. So that way when our scheduler goes to do its work, to make sure things don't get scheduled twice, we have a bit of consensus on the network. Now, if we want to go and talk about RAF, we can do that after the talk. I'm happy to go into the details of RAF, consensus algorithms, and consistency constraints, and if you actually need them or not. And the goal here is we boot all these machines, and they're PXE booting, right? So this is like real PXE. The first time I've seen PXE was like magic. It's like, so you turn it on, and the OS starts installing. We're gonna do it with all these CDs, right? So things are provisioning at this point, and what's actually happening under covers, we're actually using CoreOS iPXE server configs, and we'll look at one of our cloud configs here. So these cloud configs are very similar to what you see in like cloud deployments where you can configure a server on first boot to do a bunch of things. Here I'm just installing the Kubernetes components, mapping things to like the etcd server on the network, just some high level stuff to get the machine ready to go and be a part of our cluster, all right? So if everything is working, this fleet is built into CoreOS, and it's the machine database for CoreOS. So the fact that I see these 4 machines here, I know that I have my cluster going. There's actually 5 machines in this cluster, etcd, but I don't put it as part of my worker nodes, mainly because I don't want like load destroying my consensus replication on the network. That is really sad when that happens. So now I have a bunch of bare metal machines. Now we can start talking to Kubernetes. We're gonna get the nodes, right? We don't have any nodes in the system. So this is that separation of duties. Someone racked the machines, right? There's a team that provisioned them, and now I'm the cluster manager, right? So as the cluster manager, I'm going to add these nodes to the cluster so they can get work. And what one of these look like, and they're all, these are all checked in the Git for me. Here's one, right? I'm going to have the ID be the IP address, mainly because I didn't take the time to set up DNS. And here I'm saying that the capacity of this particular machine has 1,000 CPU units, and you kind of map it to wherever you want. And this is how much memory it has, and it's roughly a little over a gig, I believe. And here's some labels, right? So this one has, its name is node production. There's one that probably has a unique set of labels. You notice this one here has a label or role equals database. That can be used to influence the scheduler to probably run my database because this is the thing that has the most storage, maybe attached to the SAN. So we need to add these things. So I'm just going to use the Kubernetes API via the command line tool, and we're just going to create some nodes. Now at CoreOS in our production environment, we have automated systems that do this stuff for us, but I want to show you guys the details so you can get a full view. So that's one node added, and we'll add another, and we'll just add one more. So at this point, we have 3 worker nodes in the cluster, right? And one thing I need in this thing is a static route so I can actually talk to the service portal. So in Kubernetes, we have a different set of IP addresses that represent services. Now these are like magical IP addresses mainly because they don't bind to an interface, right? So that, if you look at each 0, you're not going to see this IP bound anywhere. We do a little trick with IP tables where the IP lives in IP tables. And when we see a packet hit one of the servers with that destination IP, we intercept that with our proxy, do the lookup to figure out what pod it needs to go to. This is a very common trick you do in a lot of routing setups where you want to dynamically load balance VIPs between machines, but no single machine can actually have that on its interface, handling ARPs and doing broadcast on it, right? So this Kubernetes encapsulates that pattern. So my static route is in place. So at this point, we have nodes, and we can actually look at those nodes. Get nodes. All right, so we have nodes, and they're ready for work. The next thing we need to do is we're going to schedule our Postgres container, or pod. And here's what it looks like. The interesting bits here is that we want to use the Postgres container. I don't want to pull this container. I don't have internet on my laptop on purpose, so I'm not going to pull this from the network. A lot of enterprise setups are that way. Every server's not talking to the internet. So I actually have a lot of these containers on the machines. And here I'm doing some craziness here, setting the Postgres password at provisioning time. You shouldn't do this in real life. All right, so we're going to create the pod for Postgres. All right, so now we should have a pod running. So right now it's actually got scheduled to the machine, and I knew it's going to go into that particular machine because that actually had a node requirement that it had role equals database, right? Something to influence the scheduler. I could have used the volume. So we have Postgres running, but the thing is I don't want to hit it at its pod IP because it could move in theory to another machine that met the requirements. So what we do is we create a service. So we'll create a service, services, and we'll create the Postgres service. Now that we have a Postgres service, we have a few for Kubernetes, but the one we're concerned about is this one. So this has a service IP dynamically allocated from the pool, and Postgres IP tables have been updated on all the nodes. If this works, please VMware routing, do not screw me here. PSQL, I should be able to hit this host and log in. Oh, yes. There's a high chance for success now. It went up by like 50%. Okay, so now I have this service IP. Now the thing about this service IP is that all the other apps can refer to an environment variable to find where Postgres is. It's like service Postgres port, service Postgres IP. And they don't have to know anything else about that. Kubernetes will inject environment variables into all the apps so they can find this stuff. This is automatic service discovery. The nice thing about using VIPs, if those pods move, you don't have to restart your apps, right? I've seen people do links and it's like, oh, well, we moved the thing, restart the world. You ain't got to do that here. So now that we have Postgres up and running, we can deploy the application. So now we're going to use a replication controller, and we'll just look at that really quick. So I have a few here, and the idea here is that we have the PGView app, local Memcache, and they need to be deployed together. And then we have a couple of labels that will give those things, mainly that they're in environment production, the app name is PGView, and the track is stable. And this replication controller is going to start by giving me 1. Developers wrote this new app. I'm not quite sure it's going to even work. We're going to start with 1. We'll see how you do, right? So we'll start with that. So we still met our requirement that it's going to be horizontally scalable. You just get 1 to start with. So kubectl create-f replication controllers pgview stable v1. So we create that, and replication controllers will say, oh, there's no pods in the cluster that match the specification. Let's spin one up. So we do kubectl get pods, and now we see the pod. Sorry for the view here, but here's the dynamic name allocated to the pod. Here's the actual pod IP. Here's the image that's running. It's also running Memcache, and it's up and running, and it has a bunch of labels. So just like our Postgres database, we don't want to hit pods directly and use a service. So let's create one. kubectl create services pgview. Now, I don't have anything special other than I need you to have at least these labels. If you have those labels, I'll proxy traffic to you, right? That's all we need. So this will handle things like production, stable, canary, unstable, new versions, and have one proxy still balanced between the set, the common things between them. So now we have this service. Let's verify that it's there. Get services. Sweet. Now we have a service for our app. Now all other tools in DNS only need to refer to this IP, and we're going to get the proxy. So we take this IP, And then what I'm going to do here is hit curl. I'm going to try to do what we saw in our example here, curl. And then what we want to do is make this RPC request. And I can do this with RPC version.json. Right, so it's version 1.0 of the app. This is great. Now let's test out our Memcache interaction. So the first query should be a slow query. So if I introduce a 10-second sleep if we ever had to hit the database, and the next request should be fast. All right, cool. So this is the long query happening. And then what we should do is see a big dump of all the database features. When we run the query again, it's fast. Right? So this is Memcache actually doing its thing here. So what we'll do now is like get the customer's point of view. They're hitting our service now. Sweet, this is customers hitting our service, right? And so far we like 1.0. The behavior is what we expect. So at this point, we want to go to 2.0. Well, we're not going to do in-place upgrades. We're going to roll out the Canary pattern. It's a really nice pattern. Introduce a new replication controller. It's going to put version 2 on the network, just one of them. But before we do that, let's give them a little bit more capacity to handle the load. So we'll just do a resize. So I'm going to resize the cluster, and I want to increase the replicas to 3 for this particular replication controller. We hit the button. It's been resized. And then we look at our pods. Now we have 3 of those things running, 3 collections of those servers running. What does the customer see? Doesn't see any drop packets, right? And we're still balancing traffic between them, right? So now we like what we see. We've scaled out the app, and if I had more CPUs and memory, we can go a little bit larger than that. But now we want to roll out 2.0. So how do you do that? The best way to do that is with another replication controller. We have a replication controller called the Canary. And in this case, this Canary will have a new version of the app. I'm not going to show you it because it looks pretty much the same other than the version. So we'll do kubectl, create-f, replication controllers, and what we're going to do is deploy the Canary one. All right, so now we should have another pod in the network. And if you'll notice here, let's get there. There we go. It's 2.0, right? And that's the Canary pod. And if you look at it and see what the customer's seeing, at some point, if things work and this guy gets added to the load balancer, we should see 2.0, and there it is. Right? Some customers are seeing the new traffic. Right? There's 3 stable, 1 Canary. We like what we see. The developers aren't hosting the network. Sweet. Let's do a rolling upgrade of the stable controller with a new stable controller with a new version in it. Right? So what we want now is to do a rolling update. Sweet. So every 4 seconds, I want to shrink the number of replicas in stable and increase the number of replicas in this new controller, and then delete the old stable replication controller. So what's happening in this one command is just orchestrating all the API calls we need to make to do this. You could just do this manually if you're building your own UI. So we run this, and we start to see the output of things happening here. And what we're not showing here, there's so much event data coming out of Kubernetes right now. And a lot of times you would pipe that event data to like your monitoring tools and systems to see what's actually happening on the network. Are things being scheduled? Did things get moved? Did things die? Kubernetes will automatically restart them. If it can't restart them, it will move them. It floods tons of data that you can actually use to give you higher level visibility if your CI systems are the ones coordinating these events. Right? So what should happen now is more customers should see 2.0, right? So we see 2.0 rolling through the cluster. We're still not dropping any traffic, right? So the proxies are trying to be smart here, waiting for the pods to come up, health checking their endpoints. So health checking is built into all the pods. If you have a /health endpoint, Kubernetes will hit that for you automatically to determine if your pod is ready to take traffic. If you don't have a health endpoint, it just relies on Docker to find out if your container is running or not. So it kind of gives you semantics not to have to do a bunch of glue code. You know, just the patterns for this stuff is just built in. So at this point, every customer is seeing 2.0. We did a rolling upgrade of the app with no downtime, and no one logged into any servers. And we went through this whole flow, right? So all of this is like super, super possible. And we're done here, right? So replication controller, the old one is gone. And the nice thing about this, all of this can be version controlled, right? You go through this and you start doing commits and changes to the state of your infrastructure. You can manage it all and go through history and see what changed. But you're still not checking in code, right? Just specification. And when the Kubernetes team, which I'm a core contributor of as well, when we see new patterns arise, it may need to go into a new controller. You can imagine a controller that says, I'm going to schedule this pod if the Jira ticket has been approved by my senior VP of engineering, right? We can do these workflows. And a new Go binary, maybe a couple hundred lines, we can drop that inside of Kubernetes and turn off the default replication controller and have a smarter replication controller in the network. Because these are all small and made for you to interchange. That's the end of the demo and presentation. Thank you. So at this point now, I think we're going to start passing around a mic for any of those that have questions. Just raise your hand and he'll bring you the mic.
So since you're a Kubernetes contributor and CoreOS employee, would you suggest that people spend more time learning Kubernetes versus learning the ins and outs of, like, did I waste all this time learning fleet control and the scheduling there because this will do it better?
Right, so the question there was, since at CoreOS we produced a scheduler called Fleet, and Fleet was built before Kubernetes hit the scene, and we built a low-level implementation of what a scheduler needs, the foundational bits. And the goal was to build some of the user workflow stuff we just saw here that Kubernetes has. Kubernetes hit the scene. We were like, that's it on that. We don't necessarily need to build that functionality. But what you'll notice is, in the way we do it is we use Fleet to deploy Kubernetes and keep it up and running. So Fleet is still the machine database. It still has utility there. And for a lot of people, Fleet is all you need. You have some unit files, and you just say, hey, Fleet, put these unit files on my server. I don't really need like 99% utilization on my servers, if you can ever get it. You don't need all that. So it may make sense for you just to stick with Fleet. So we continue to invest in Fleet to be a nice, low-level, basic scheduler that the majority of actually organizations, that's all they need. Kubernetes is the thing that kind of gets fancy. We do see a long-term vision where you don't even want to worry about low-level scheduling details like that. You just want to define the state of the cluster and let the smart components work things out. So that's kind of where we see the long-term vision there. We support both because we need both. Great question. Any other questions? There's another one there.
Hi. So I was kind of wondering, how does this scale across different machines? Because you had all of this running on one machine, but in terms of high availability, that's a concern that I would have as a sysadmin to make sure that this runs across multiple machines. So in case, assuming you were running this on two physical servers, on just one physical server, I should say, it craps out, you have all those containers down. How do you work with?
So I actually had 5 virtual machines there to kind of give you that feel. Even though they're on my hypervisor, my local Mac, there was 5 machines part of that cluster, right? So what happens in Kubernetes world is that if one of those machines goes down, so let's talk about high availability. On the back end, there's etcd, and that uses the RAP protocol to kind of replicate data real time. So we make a lot of trade-offs on some performance bits to make sure that every write that comes in, we replicate to the other members in the cluster, or at least until we get to the majority. In a larger setup, you would probably have 3 to 5 of those nodes, and that would be your HA story for the data backend. Everything else in Kubernetes, everything else is stateless. None of them save data to the local disk. They all go to etcd via the Kubernetes API. So the next part is the Kubernetes API component. It's the thing that you send commands to, and it's the thing that the other components watch to see if any state has changed. Now that component can go down. If it went down, you just can't schedule new work. None of the pods stop. And that thing can float anywhere in the cluster. We use Fleet to just ensure that it's running somewhere, right? So that handles the HA story there. And it also has code to do master election, meaning if you have multiple API servers contending for the same resource, they'll elect a leader, and only one of them will handle the role of actually updating the backend. If it dies, there'll be a race for a new leader. When it comes to the pods and everything else, those things are all local to the machine. So remember, these replication controllers are in a very similar situation as the API server. You just need them running somewhere. If it goes down, spin up another one. The replication controller's job is to just make sure that when the Kubernetes report, like, yes, I'm running my pods, if they ever stop the liveliness checks, the replication controller springs into action, finds another node for that pod, and reschedules your work. So if you pull the plug on one of your servers, the replication controller will notice that things have timed out for that set of pods and schedule them somewhere else. If it can't schedule things like the database because you don't have a machine fit to run a database, you'll just see logs, can't schedule, can't schedule, can't schedule. Then you need to wake up and schedule it. So it tries to handle a lot of those things. Kubernetes is built very much after the pattern of Borg at Google. Same people working on it. They need things to be HA here. I mean, they really try to get to that, 5 nines or better situation. So all that stuff is kind of built into the system. Good question. There's a question here.
Is there any plan for supporting console rather than only etcd or?
Yeah, so right now, so the question was, is there any planned support to support console in addition to etcd? And the answer there is that etcd is only used as a key value store in consensus. So console definitely has that feature. Zookeeper also has that feature. The Google team internally, Chubby is built very similar to etcd. It doesn't have all the features console has, like not built into that. They build their stuff into front-end proxies. So you may have a DNS front-end, you may have a ACL front-end, and you keep the consensus thing very light with no features, right? You don't want this thing doing any additional thing other than handling consensus and key value storage. That's probably why they picked etcd initially. But since it's an open source project, I think it'll be fair, just like we're doing at the container runtime, we're adding support for Rocket. So you'll have a choice of Rocket or Docker to schedule to. And I think it would be fair to have your choice of backends that you use for your data persistence. So I guarantee if someone did the work to make it, because it's already abstracted pretty well today, you only need to probably touch 1 or 2 files to probably do the work and support console, right? It's just that they have a preset of things that just come out of the box that just work, right? Good question. Any other questions? One up here in the front. Was it a race condition here? You win.
So you showed all the clients just kind of randomly going to the new version. Is there a way to direct certain clients, like beta customers or something like that, to the new version of code?
I guess you could do that, but that would be a slightly different thing. Create a new service IP that follows only a specific set of labels, right? And then when someone hits that IP, it will only do a lookup. And the way that would kind of work if we did something like a kubectl git pods, right? That gives us all of them, right? And that's what the services do in the background. But we could give a label query. We could do something like this. I'm gonna make this smaller. We could just say, I want things that are stable at this in production and track is stable. Right, so let's do this. So that gets us for the pods. And now if we wanted to pin a new service, we can just give it a set of labels, Canary. And you only get 1 pod, right? So this is what's nice about those things. So even though you have a global view, you may want to pin a few customers by saying, we're going to give you a new service IP and a new URL, a DNS name that points to it, and then you can lock someone in to a set of pods with a set of labels. This is why I think the label thing is the most powerful part of Kubernetes, because you can make decisions after the fact. You can say, oh, we do need to have, Joe locked into that. Just do some more labels. Shrink the labels, grow the labels. And the whole system is just achievable by just doing that. I think that's a really easy thing to do. And you see how easy it was to do, just pop a new service in there, and you're good to go. Cool. Another question there.
So what's the road? I mean, this is really exciting stuff. We're kind of like in the scheduling things with Chef world, which is painful. What's sort of the time frame for this? Like, what's your roadmap for saying like, hey, this is actually like a thing, it's stable, and like, let's go do this.
Cool. So the question was, what's the roadmap for stability for all this? Should you run it right now in production? No, you shouldn't. Unless you want to get to know me on IRC, I will help you, but I will laugh and giggle behind the screen. The good news is there are a lot of startups that actually run this in production. They're just crazy like that, right? It's part of their burn rate, like burn infrastructure, burn their cache, all that. But Google has a nice roadmap on this. In June, we're going to mark 1.0 stable for 100 nodes. We're going to be realistic with ourselves. Then, at the end of the year, we want 1,000 nodes. And this is going to firm up the API, and it's going to firm up the patterns, and it's going to allow us to catch things. Right now, internally, Google has 30 to 40 engineers working on this full time. This is outside of the people that run GKE, which is the hosted version of Kubernetes. There are parts of Kubernetes now that power some of App Engine, like the kubelet. When you drop that container in there, you're dealing with the kubelet locally. So they have a big incentive now that this is now going to be part. This same Kubernetes we're using, they don't have a different version of Kubernetes internally. Same one is being offered to GCE customers, right? This is on the, like the billion-dollar product roadmap. They're not trying to play games with this one. So we're being honest as we roll this thing out. For most people, it does take a long time to migrate to all of this stuff. So it's probably a good idea to get it in a small part of the infrastructure, maybe dev or testing, learn the components, learn how to operate it. We're starting to see a lot of tools that integrate and monitor it. Get familiar with it, right? Play with it a little bit. And then track the stability pipeline. And I honestly think in about a year and a half here, we'll have something pretty solid. Because to be honest, underneath the covers, it's not doing a lot. Seriously, it's not like OpenStack was trying to engulf the data center and then you can't upgrade it. Maybe some people can, but I couldn't. So great question, but yeah, I think you should start kicking the tires with it. There's a question there. How are we doing on time? Okay.
So I didn't quite follow exactly how you deployed etcd at the beginning, whether it was managed through Fleet or through Kubernetes. But like, what does it kind of look like if you want to do, like, can you do a rolling upgrade of the etcd layer if you want to be able to upgrade that everything else is depending on as you're interacting with it?
Right, good question. So the question was, how do you do rolling upgrades of etcd when everything else depends on it, right? So the right way to deploy an etcd cluster in real life, you're gonna have an island, 3 to 5 nodes. You have this island. If you don't have the island, I will laugh at you. You're gonna have problems. You build this island, and the way etcd clients are set up, they usually have a list of all the nodes. You can get this from DNS SRV records. You can get it from a discovery endpoint. So since they have a list of all the nodes, one way that we automate restarting etcd is we have a small, let's say a 5-node etcd cluster, and we have this tool called Locksmith. And Locksmith's job is to grab a lock on etcd before it reboots the node. So you can imagine having that etcd domain, getting the updates of CoreOS, and then trying to coordinate reboots of themselves, right? You gotta be careful because you could get in a weird state. If you lose the majority, right, you go and grab a lock because all the nodes are up, you got consensus, you have the lock, and you reboot yourself. You're on the way back up. There's still a majority, right, in a 5-node cluster for someone else to say, oh, you're back, you released the lock, but you haven't caught up to the replication state. The other guy like grabs the lock because that will work, the majority, and now you have 2 nodes that are not caught up in the replication. Now, depending on timing, you can be really screwed where you're gonna have a bunch of elections and people will be out of sync here, right? So there's ways you can kind of mitigate that, but the idea with etcd is that since you have RAP and you have the replication, every client needs all the members. This is just how it works because any of the members in etcd will proxy you to the leader. So in Raft, you have a single leader system. None of the nodes write independently. They all forward a leader, and they elect a new leader. So if one of the leaders goes down, they have an election, a new leader is formed, automated by part of how Raft is designed. And once you have this new leader, if you happen to hit one of the followers and you want a consistent read, then you will be forwarded to the leader and go through a round of consensus before you get your read. If you want to write, you're always forwarded to the leader anyway. So this is how we mitigate this. Does that answer your question?
I think I need to read a lot more documentation.
So one thing you can do, I think, it's not a lot of math in it, but the Chubby paper. There's a white paper from Google called the Chubby paper. Read it because they do talk about a lot of the operational aspects of Chubby, right? And you can find me afterwards and I'll walk you through it. Cool. Any other questions? I think, Jeremy? Please stop us when we're out of time.
Cool. So you mentioned caching as a story for label queries. Is that something you guys intend being on the roadmap for Kubernetes or it being a workflow outside of?
So I've built proxies, and I'm actually in the middle of building a Lua module for Nginx, where the Lua module will talk to the Kubernetes API to do label queries, right? And then just populate the backends at runtime, right? And most of these systems, whether you're using DNS as your service discovery, you're gonna have some latency between how fast do you wanna fulfill requests, and are you willing to wait for that hop? So you gotta make that trade-off. By default, that service proxy is just like a nice get starter thing, but it does make that request every time. For some people with web requests, that's probably gonna be a fraction of the total lifecycle of that packet. But in some cases, you may just want a system where something like Nginx or Juniper piece of equipment does label queries on its own, and you just decide your caching strategy. So if we ever build something, I'll probably be building something on the community side. I actually have a Kubernetes-specific load balancer I've written in Go that does this. It does label queries on your behalf, and it caches it a little bit. And you just imagine having settings like, cache it for 3 seconds, maybe cache it, or you can do watches, right? Remember, the API server does support watches, so you can actually watch to see if there's any events that change. So cache until you get notified that there's something to actually go requery, right? So these patterns are all encapsulated. Some people do this with etcd today. Have things update and then just watch. Does it change? So that makes caching a lot easier to deal with if someone can tell you there's an actual change. So you don't have to actually poll, right? So this is something that I think you'll start seeing a lot, especially when we hit 1.0. The API will be nailed in stone. It pretty much is now, and you'll see more tools built around it. Good question. Did we finish like super early or something? Yeah, I did, huh? Cool.
If you have a pre-existing load balancer infrastructure in place, so big IPs and what have you, how does this integrate with that in terms of putting things in and out of service?
Cool, and so this is why I'm building a lot of tooling around this. Like I actually have like big patch for like the Juniper gear. I call this the real networking gear. Like the cloud is like fake networking, right? It's like, dude, no, that's not even what we deal with in real life. But the nice thing is, since the APIs are so clean, unfortunately for a lot of networking equipment, the APIs aren't so clean. So you end up just building a little bit of glue code, right? I have some things at home. I have a nice little Juniper switch at home that does L3. And what I can do there is like, I can talk to these APIs for either Flannel or Kubernetes, get the set of pods, and then just SSH in and do the right commands that I need to. So you're probably gonna have to see some modules there, maybe a little bit of glue code. If you're already automating things, the nice thing about this system, you're not like scraping ifconfig commands and all this business. You can just straight up talk to the Kubernetes API. It's gonna give you a well-formatted list of returned items. Like if we do here, YAML, if you wanna see this in YAML, you get all the data in YAML if you want it, right? So, or you can do JSON. So this is like, now it's just easy to program those things. So in GCE, we do exactly this. There's automatic integration with their load balancers just because it makes the right API calls. And there's automatic upgrade integration with their routing layer. So you can totally do this. If you have an API for your network gear, honestly, like 150 lines of Go code will be populating those things. So good question. I think we're out of time here. I'll be outside if you guys want to find me. Thank you guys for attending.